Good day, and welcome to this presentation by group number 26 on CAE Use in Mouldings and Mould tool design. Take a look around you. Look at the items that you use every day, the items that you have around you. Do you think molding and CAE played a big part in the manufacturing of those items? Well, the answer to that question is, yes they did. So you may ask, what are molds? And according to the Oxford Dictionary, a hollow container used to give shape to molten or hot liquid material when it cools and hardens is a mold. And now you may ask, when did we make the very first mold in the human history? Well, for that question, let's take a look at the history of molds and molding industry. But first, let's travel back to 2000 BC, where the first evidence of man-made molds were discovered. Using stone spearhead molds, we were able to make spearheads to be used in wars. But as you can see, the lack of details is quite evident in this very first mold. Now, somewhere between 1400 to 1000 BC, we were able to add more details to our molds, creating better spearheads that were used during hunting and possible wars at their age. But it was not until 1868 that we saw the very first modern mold being used by John Wesley Hyatt to make billiard balls at his age. And 4 years later, alongside his brother, he was able to make the very first injection molding machine. Oh, what a historical date. And in 1946, James Hendry was able to build the very first screw injection molding machine. Another historical date. And that brings us to today, 2015. And molding is in every single industry you can possibly think of. From making items as small as the screws and bolts, to making things such as spoons or even cars. So you might ask, how do they design molds? Now that we know where molds come from, how they were made, and what they're used for, how do we make them? So this is where computer-aided engineering comes into play. Computer-aided engineering is generally referred to computer-aided design, computer-aided manufacturing, finite element analysis, as well as computational fluid dynamics, and they all come under the large umbrella of computer-aided engineering. Computer-aided engineering has many different software packages associated to it that allows engineers to perform many different tasks for an engineering project. And let's take design for an example. Using computer-aided design, engineers can create, modify, analyze, and optimize the design of a product. This can increase productivity, quality of the design, and communication through the documentation. Now we move on to computer-aided manufacturing. Computer-aided manufacturing allows engineers to control our machine tools to create the best possible products that we can. Using this, we can increase productivity, precision, and consistency of our design. We can reduce energy consumption as well as the wastage of raw material. And of course, who can ever forget about finite element analysis? This method allows us to simulate how a product behaves under certain circumstances and forces. We can simulate this and find out if our design has any flaws, and from there we can improve our design and strengthen it so that it can perform the best at any possible condition within its working conditions. And now we move on to computational fluid dynamics. Fluid dynamics is probably one of the most interesting and undiscovered parts of science. And computational fluid dynamics has allowed us to simulate fluid flow and predict certain properties of fluid and certain events that happen during a fluid flow. Of course, the biggest use of computational fluid dynamics is in Formula 1. Now let's have a look at how CAE has changed the molding industry, and it really boils down to one simple concept: design right the very first time. In this age of manufacturing, where quality and time are of utmost importance, using the conventional trial and error to make the mold and optimizing them is not really efficient. Because after all, how many molds do we have to make until we get the optimal mold, right? So we needed a method to simulate and find out how the optimal mold should look like before we actually manufactured it. Because at the end of it, most of the cost is in the manufacturing of the mold. And that's where CAE came in, because CAE allowed us to simulate and design the mold to optimum levels without actually creating the mold. So let's have a look at how CAE changed the molding industry. First of all, using CAE, we are able to analyze the flow simulation, the cooling simulation, structural analysis, and the material orientation after the molding process has been completed. So using CAE, we are able to reduce the tooling time, increase the quality of the total product, and of course, acquire the optimal mold design before we even create the mold. So we only have to do it once, and we're going to do it right. So what does CAE reveal that allows us to achieve the optimal design? Well, a lot of parameters such as pressure, shear stresses, clamp force, temperature distribution, and all of these important parameters allows us to find out what is wrong with our current mold design and how we can improve it. So using computer-aided design, we can design the part that is going to be molded first. And we can take the design to a software such as Mold Flow or internal features within Creo Parametric to design the optimal mold that we're going to use to mold this product into real life. And we do that by determining molding processes and also the parameters such as the position of the gates, runners, the injection velocity, and also injection temperature, which are very important parameters in the actual molding process. This in turn will allow us to create products of incredibly high quality and also ensure that these products will look what they're supposed to look and do what they're supposed to do when they are fully molded. And here it is, ladies and gentlemen. This is how computer-aided engineering has changed the molding industry. So let's have a look at how the analysis is actually performed. But first of all, we need a CAD model of something that we're going to mold. And then following that, we have to import that design into a mold flow software using file types such as STEP or IGES. And then we need to create our simulation to set it up. For that, first we need the physical models, where we have to firstly define whether it's a 2D or a 3D model. And then we have to select our material as well as the boundary conditions and constraints. Under the mathematical, we have to select the coordinate systems, computing units, as well as the geometry boundary conditions and constraints. And of course, under the numerical model, we have to select the element type, the mesh density, the calculation parameters, and the convergence criteria. This information would support the pre-processing of the CAD design and further generate a CAE analysis model. Before conducting analysis and simulation, the users need to specify the detailed molding information, process parameters, and molding conditions. After simulation and analysis, the calculated results need to be analyzed and evaluated. If the results and solutions are not satisfactory, the suggested changes regarding part geometry and structure, mold structure, and molding conditions will be made for the next round of computation. The process is iterative until all the design requirements for moldability, productivity, and product quality are met and an optimal solution is obtained. Oh, now it's time for us to look at a case study and see how CAE can be used to simulate mold analysis. This little cute box that you see over here is designed by ourselves. And first of all, we have to select the material that we're going to use to manufacture this little cute box over here. Do you know how hard it was to make the heart on that side? Either way, first we had to select the number of gates. And CAE has this feature that we can automatically calculate all the gate positions. Now, since we've done this simulation before, I'm just going to load the results. And we're going to look at how the results are going to look like. we're on the sad side for now. Now first of all, let's make an animation to see how the flow looks like. You see the red part shows the gate where the material first enters. And as you can see, the last bit of the mold that gets filled up is that bit on the hearty side. Well, the lovers get the least. So we are expecting a bit of problem in that little bit of the hearty bit. So let's take a look at how the results are going to look like. This is the moldability of the part. As you can see, the part is perfectly moldable. Now we're looking at air traps. The design is made in a way that we're going to expect some air traps which are potentially problematic. So CAE is a very kind software, and CAE, well, Creo Parametric, is going to tell us what to do so we can improve our design to avoid air traps. Very kind of you, Creo. Well, after kindness of Creo, we're going to look at some of the other parameters that Creo has to offer for us. What you're looking at right now is a pressure distribution around a mold. We can also look at the temperature distribution as well as a volume shrinkage, which is a very crucial part and parameters in molding. What you're looking at right now is the velocity vector of the material flowing into the mold. Following that, we can look at the gate distribution, but of course we have only one gate, so it's quite obvious. But this is a very important bit, the clamping force. And as you can see, it can be shown in a graph form, so it's easy to analyze and easy to understand for design engineers. In addition to that, we've got a graph for the flow rate. Now, we know how the simulation and how the molding for one gate is going to look like. So let's look at how two gates is going to make our molding look better. So we're going to select two over there, and we're going to press the calculate, and YOLO, we get our results. Preliminary ones only. So what I'm going to do now is select the results from the simulation we've done earlier with two gates, and we're going to see how the animation for the flow of the material is going to look like. Again, the two red spots are the gate positions, and the last bits to get filled are again on the hard side. Lovers always get the worst. Well, either way, now we see how the actual molding process can be simulated using a typical software package such as Creo Parametric. Now it's time for us to move on and talk about some of the advantages and disadvantages of using computer-aided engineering in the molding industry. First of all, safety. Of course, safety is the biggest factor in the manufacturing industry, and CAE has been able to increase the safety of molding industry by margins. The biggest part is the economic savings. Of course, since we're not making loads of molds and using trial and error, we're getting a lot of money saved from that, right? Applications. Complicated features can be created and modified pretty easily. That's why these days we see a lot of weird products out there. Of course, now we can see how the molding process takes place, and of course, seeing is believing, right? And in addition to that, we are able to calculate the cost of a molded part quite fast now. That helps us in the quoting of product costs. Now, since everything is not perfect, let's look at some of the disadvantages, and this is probably one of the shortcomings of some of the softwares. The materials might not be specified. This is where the biggest problem is. Garbage in, garbage out. We have to be careful what assumptions we put inside the software, and of course, CAE adds to the computational cost. But all in all, we do believe that computational aided engineering has changed and revolutionized the molding industry for the better. We sincerely hope that you have enjoyed this presentation by our group, and you can find the references where we found material in our next few slides. This is group number 26, and thank you very much for watching our presentation.